case around water, there's also a lot of factors. Perfect. So we're excited to have Giancarlo in the Arteche,
Thank you very much for the introduction and for the invitation here. So, yeah, I had a sudden change of heart about the title because the title was Sales Conjecture 2, but then I realized that the motivation that I'm going to start with, that it's more or less half of the talk, will be about Sales Conjecture 1. So, yeah, I had to change the title. So, yeah, the part of Sales Conjecture 1 is joint work with the schedule, but that was, well, it's typically published this year, but it's pre-pandemic work anyway. Just a standard time for publication of that. And I cannot stress this enough. The part for Sales Conjecture 2 is work in progress. So I hope I will be able to tell you what we expect, what we think we can do, and what we have done. So let me start with motivation. Well, of course, this has a lot to do with last talk. So I can be brief in some part, but I still want this to be self-contained, so I will repeat a little bit of what I already wrote here. So let me start with notation. So K here will be a field of characteristic 0, even though the first part is true for any field, but I don't want to start about that. Let's just stick to fields of characteristic 0. So KQM of K will be the Q's theory group. Okay. Okay, of course. And so if I take Z a K variety, then I can define these groups NQZ K, which are defined as well, the groups generated by norms and K of the K theory of L for the fields L such that Z has a rational point. So this is a subgroup of the Miller K theory of K. So what's the point of these norm groups? Well, they are defined so that you can have a generalization or actually a weakening of the property of having rational points. Okay, that's how you must look at these groups. So, for instance, if you do have a rational point, then you can actually see that, well, this norm group will immediately be the whole K-theory group. That's quite easy to see because, of course, you can take that rational point and the norm will just be identity and done. So that's the easy sense. And the other way around, so what about if I have the equality, what can I say about rational points? Not that much in general, but next. Oh, yeah, of course. Okay. None if you do have rational points here. Very important. And yeah, the other side of the question, if I do have equality at the 0, so if I do have equality here, then, as you already explained in last talk, this is essentially having a zero cycle of 2. Okay, so Z has a zero cycle of degree 1. So that is as close as we can get with these norm subgroups, as close as we can get to having a rational. So this is indeed a weakening of the property having a rational point. And the higher you go with the degree Q, the farther you go away from arithmetic, from rational points, and the more you get into K theoretical properties. That's the idea. So we use these norm groups to define these properties given by Kusumaki. That tell us that so K is CIQ field if, so this is the definition, for every extension over K finite extensions, and for every hypersurface Z PML, so hypersurface of degree degree d with d to the x more equal than n, so of degree really small with respect to the amount of variables we have, then we do have this equality of, we have that the norm group is the whole K theory. Okay, so this is a generalization and the weakening sense of the property Ci. So as Diego explained before, Ci implies Ci0, for instance, because instead of rational points, you are now asking for 0 cycles of degree 1. So this is with the property done with Ci. And the conjecture by Kusumaki was precisely that K is CIQ if and only if the chronological dimension of the field is smaller or equal than I+. And once again, I should recall what is known about this conjecture. So we know that the conjecture is true for I equals 0, and this is essentially explained by the block-Kato conjecture. So this was proven by Kato and Kusumaki in the same paper when they introduced this. At that time, it was dependent on the block-Kato conjecture, which hadn't been proved at that time, but now it's already a theorem by Blavatsky. So the conjecture is true for I equals 0. Although, that's a problem, the conjecture is false for I equals 2. Firstly, this is Mercury. And so yeah, he exhibited essentially a field, some field K2 with chronological dimension 2, but K2 is not C2 0. So that's I equal 2 is essentially false, this conjecture. And then this was the same techniques were used by Couleton and Amada for I equal 1. So same kind of counterexample. And here you have that dimension of a certain K1 is 1, but this field K1 is not C10, which is essentially the only property you had left. Because if you expect this conjecture to be true, you have C10 and C01. There's nothing more you can do with chronological dimensions more equal than 1. And yeah, so C01 is true because of this, C10 is not. Okay, so this is the worst thing you can get. Because as Diego explained last time, so you expect to have CIQ. If you put I equals 0, then you're good to go. You have to block out conjecture. And the more you take away from Q, the more you add to I, the less K-theoretic you are, the more arithmetic you get. And that is, of course, the difficult sense of things. Going from algebra to arithmetic is difficult. So, okay, so we're starting I equals 0, I equals 1 is not true. Great.
The first example is actually the one with the invariant 6 field.
This one here?
Yeah.
To be honest, I really don't remember. I concentrated on this one.
Yeah, I actually have never looked at the actual example.
Yeah, it's a horrible field though. That's fine. That's what Diego told us in his talk. These fields are absolutely horrible. You will never see them in your life doing normal mathematics. So yeah, that's why the two directions we could go is, okay, let's deal with usual fields. And that was Diego's field. The other question you could ask is like, okay, how can we replace these properties so that we do get something that is true for every field? At least of characteristic almost every field of characteristic. Okay, so this is what I want to tell you because in the previous one we did with Diego, we came up with the following idea, and by we I mean Diego. So yeah, the original idea was, okay, let us replace hypersurfaces of degree D with D is more or equal than N, so we're thinking about I equal 1 here. So that's why I insist on this one. We concentrate, since this is the first case where this is false, because I equal 0 is okay. Let us concentrate on I equal 1, let's see what we can do. And okay, let us replace hypersurfaces of degree D with D is more or equal than N by homogeneous spaces. That was the main idea. So homogeneous spaces tend to be classified or understood via cohomological terms in general. So maybe there's a chance that with homogeneous spaces we can actually describe completely, we can characterize homological relations. And it turns out it works. Okay. So let me give the definition first. I can actually state a theorem. Okay. Of course you define the exact same thing, but I have to write it anyway. So, definition. So we're going to say that K is CQ, and I replace the one here by HS for homogeneous space, if, well, for every L over K finite extension, and for every, not hypersurface anymore, so for every homogeneous space Z of a connect linear K group, no, L group, sorry, we're over L. Connect linear L group. We have that the norm group NQ Z over L is the whole K theory group of L. Okay, and then the theorem would be the following. Yeah, K is CHSQ if and only if the cohomological dimension of K is more or equal than Q. So, in a sense, the motto here is CQHS replaces C plus Q.
Do you allow homogeneous spaces under non-affine groups?
No, not impressible. We really. Yeah. Yeah. It's it. Okay.
Any restrictions on standardizer?
No, none. Although, of course, this is even only if, so of course you would expect that you don't need every homogeneous space to get homological dimension Q plus 1. That is indeed true. So there are two families you can consider. The first one would be, well, let me state some consequences of this, and I'll come back to that. But you can have some subfamilies, and then the interesting side is the other side. So if you have homological dimension Q plus 1, then you really get every homogeneous space. No assumptions on the side. Okay. Okay, so let me state some consequences. Let me concentrate on the case Q equals 1 first. So what do we get here? Well, if Q equals 1, here we are in homological dimension 2. Well, it's more equal to 2. So in that sense, you get the theorem is showing you that if you have this homological dimension, then for every finite extension over K, right? And for every, so I'm going to take A over L as central simple algebra. And then for every SL1A torso Z, well, you have the consequence of the definitions. And Q Z over L is equal to, and here's not Q, that's one where Q equals 1. So it's Q equal 1. And 1 Z over L is the whole K1 M, sorry. And L. Okay? And this is just L star. So if you think for a while what this means, so SL1A is one particular case of algebraic group, torsos are one particular case of homogeneous spaces, so this is just a consequence. But when you start thinking about what does this mean, what does this mean? When do I have points over such a torsor? Well, and what does it mean that the norms during the whole thing? What you're actually saying when you write it down like slowly you get the conclusion that for every L over K, for every central simple algebra over L, well, the reduced norm from A star to star is surjective. Okay, so I'm saying that when you have convolutional dimension 4 equal to 2, you have the surjectiveness of the reduced norm, and this, of course, is the result by Susan that characterizes convolutional dimension 2. Okay, so it goes both ways. If you have surjectiveness here, you get convolutional dimension 4 equal to 2, and vice versa. So that's one family of homogeneous spaces you can look. SL1A torsos for central simple algebras A over L. That already gives you back convolutional dimension 4 equal to 2. And you can actually prove this for Q different from than 1. So that's one from you can take. And the other one we took, with which we proved this direction over here. So yeah, it's on this one. It's yeah.
Sorry. For SL1, do you really need all of SL1, or can you just take separate Brauer lines as your disease?
Yeah, several Brauer. Yeah,
just that.
Yeah, that's nice. Okay, sure. And the other one we took was which actually goes a little bit back to C1Q. That's a nice thing. It's torsos under normed tori. You take normed tori, then you will see that they have exactly the amount of variables you need, and you can actually recover back the convolutional dimension over there. So it is hidden in the proof from here to there that actually C1Q implies convolutional dimension Q. Also, because torsos under normed tori are hypersurfaces of the region. Anyway, so this is just motivation, so I don't want to extend myself a lot in this part. But so yeah, let me just take another nice consequence, because this theorem, the nice thing about this one is that unified and generalized somehow a lot of known results in the literature. For instance, this one absolutely. Another consequence in Q equal 1 is the following result: that you take K, a p-adic field, or a totally imaginary number field. So these are fields of convolutional dimension 2. Then K is C1Hs. Okay, and this was a result already known by Peter. So we actually reproved that in a more general setting. And then, for instance, and this is the point where I really want to make an emphasis. What happens in Q equals 0? So if Q equals 0, then we're not anymore in convolutional dimension 2, we're in convolutional dimension, convolutional dimension of K, Ct of K, or equal to 1. What do we get in these cases? Okay, let us write down the whole thing again. For every L over K finite extension, for every homogeneous space, Z under a connected linear L group, we have that N0 Z over L is the whole K0 group of L. In other words, as I stated before, Z has a zero cycle of degree 1. Okay, so this, let me put it in parentheses, so now replace zero cycle of degree 1 by rational point and get what is known now as Steinberg's theorem, but which is also Serre's conjecture 1. Okay, so we did not get Serre's conjecture 1 from our result, but we did a weakened statement that replaces rational points by zero cycles of degree 1. So yeah, what's the point of weakening a result that's already known? Well, here's the upshot. So weakening self conjecture 1 to 0 cycles yields a generalization of, well, the same conjecture to higher homological dimensions. An arbitrary high. But what you have to pay instead of having properties with rational points, instead of having single cycles, instead of having points in varieties, you have to work with this higher K theory. So we have to higher homological dimension using higher K theory. So this how we came to this problem. This is how we came to the title of the talk today. So we replaced C1Q with this nice property of homogeneous spaces, and we realized that a consequence was almost self-conjecture 1, but weakened. So now the obvious naive question. Yes, so now the obvious question is, well, what about self-conjecture 2? Can we say anything similar to this? And yeah, similar good, right? Oh. Great. So now, so let us talk about higher versions of sense. So, and let me start, of course, by stating the conjecture. I assume almost everybody knows it here, but anyway. So conjecture 2 says, well, if you have a field of homological dimension 1/2, then for every principal homogeneous space, Z under A semi-simple, simple connect. Algebraic, yeah, they semi-simple K group. We have a Russian. So essentially, every torsor under a semi-simple dimensional group is true. Okay, that's another way of stating it in a short version. But I wanted to write it with rational points because now with rational points, you can change rational points to zero cycles of V1, and then replace zero cycles of V1 by K theory, and then change 2 by Q plus 2, and get what you would expect. So, in order to do that, let's give a new definition. So the new CQHS is the following. So K is CQSC for simple connector. If, well, same thing, for every finite extension over K, and for every principal homogeneous space Z under A semi-simple, simply connected L group, we have that the norms coming from points where this variety has rational points do generate the whole K theory group of them. Okay? And okay, anyone that works with semi-simple genetic groups knows that at some point you have to come up with a classification. So usually nobody can prove anything using just the fact that it's semi-simple and connected. So I have to define the very same thing for a given type. So for lambda, a given type in the classification, of semi-simple, simple connected groups, we say that K is CQ lambda if, and here comes the technical part, you would expect, like, say, any semi-simple, simple connected group of type lambda. Sure, but what you would expect, whatever I put here, you would expect that K would be CQSC if and only if it is for every lambda. So if I want that to be immediate, or at least easy to prove, I have to have the following technical condition. So, well, of course, for every element, finite, that doesn't change. For every finite extension node, and for every principal homogeneous space, Z of under. I guess G will not just be semi-simple, or you would expect typically an absolutely almost simple group, but I'm going to need to take violent sections. So G will be a violent distribution of a certain G0 or something, and G0 will have the property of response. G0 and absolutely almost simple and simply connected M. And then for those, you prove the obvious equality of the norm group and the whole K field. Yeah, of course. Of course. I just ran out of space. But yeah, I shouldn't put it. Okay. M group of type lambda. You have NQ Z over L is equal to the whole K theory of L. Okay?
So was the final.
I was expecting that. Yeah. There are two choices actually. You can either choose just finite extensions, so fields, or choose Étale algebras, which will give you products of value restrictions as you would expect. So the point is, you can prove a tiny lemma. It's relatively easy to prove that if you have a product of varieties, and for these two varieties, you have this equality for every extension of your field, then you get the same thing for the product. Having this, that's just a technical tiny lemma you can prove. You can either plug in here Étale algebras, then not even care about if it's immediate at CQ lambda implies CQSC, you have it for every lambda. And you use the lemma in the proof of CQ lambda, or you define it for fields, and then in the equivalence here, you use the lemma. Anyway, yeah, so it's irrelevant. We haven't decided which one we're going to put in the actual definition, so I'll just leave it like that. I won't say what M is, but go for it. So the immediate remark was precisely that you can prove that K is CQSC if and only if K is CQ lambda for every lambda. So if you have it for every type, you're good to go. Okay, so now we have reduced the question to the classification. When you have to work with these functions, otherwise you cannot. I mean, a general simple connected group will be a product of these guys, not of just absolutely simple groups. So you have to take care of those, and that brings a lot of trouble. I mean, it's doable, but it really brings a lot of trouble. Okay, so now, now I can actually tell you, as I told you at the beginning, what we do expect, what we think we can do, and what we have done. Okay, so let me start by the expected result. So conjecture. The conjecture would be, well, the cohomological dimension of K is more or equal than Q plus 2, if and only if K is CQS. That's what we expect. So this is the higher version of Self's conjecture 2. Okay, plug K equals 0, and you get essentially Self's conjecture 2 with 0 cycles of degree 1 instead of rational ones. Okay, so this is easier than Self's conjecture 2 in some sense. Now, what we can do. So we have done, I mean, this is the only part that is written completely in full detail, and we are pretty sure there are no mistakes. So this I can state as a theorem. So first part, as before in self conjecture 1, we don't need every homogeneous space to get an if and only if. So one can actually prove that the homological dimension is smaller or equal than Q plus 2 if and only if K is CQ, and here you plug 1AN. Okay, so let me just remind that this type over here is essentially this kind of thing. Okay, so this is a version of what you could call a higher Suslin theorem. Okay, so it's once again the theorem from before that reduced norm characterized with homological dimension 2. Now you get a higher version of this theorem. You can prove that if you have homological dimension 4 equal to Q plus 2, you get, instead of rational points, instead of zero cycles of degree 1 in these kind of homogeneous spaces, you get, well, the surjectivity at the level of the KQ group of K theory. And the other way, you can recover homological dimension, you can characterize homological dimension by looking at these norms. So that's one part of the theorem, and there's a second part. So once you get that if and only if, so you forget about the if part. And now you start proving always from homological dimension Q plus 2, you start proving stuff on the other side. And we do have this result in this sense. So K is CQ2AN. And hence, just CQAN with no specifications. So these are the other type of forms of gradient. So it was SU of a vibration form over some central simple algebra image. Okay, so we can prove the same statement for these 10 groups. And so essentially, you can prove it for any form of S. Okay, and now for the last part, so that is what we expect. That is what we have proved completely, and I want to say in progress here, this is what we expect. We think that it's provable, we will do it, but it's being written. So EN, CN, DN, and I'm going to put greater than 5 because I want to avoid triality, but D4 without triality should be okay. So the classic ones, F4, G2, and E8. That's the news. That would be the interesting one. Because the other ones, so why do we expect this? Okay, so then we go to the third part, last part. Ideas. Proof. So here I'll try to explain why we expect all this. I think it's true. In particular, how we did the whole first theorem. So let me start by a main vague idea. This is really what drives us. The idea is, well, just follow the known cases of self-conjecture 2. Of course, you start there. You know these cases, you try to generalize those. And what is known? Well, you get the one we saw by Bayer and Parimala that actually does all of the above, but E8. So all of this is by Parimala. You expect to just follow their proof. Well, E8, that would be Gilles in the split case. Split case, and very important, but not a problem for us, and for 0 seconds of degree 1. So, so self-conjecture 2 for E8 is not proved, not even in the split case, but the weak self-conjecture 2 is. And prove that in the split case, E8 has the cycles of degree 1. So we're done with this. But I haven't finished my sentence. That's a parenthesis. I haven't finished my sentence. So yeah, of course, follow the known cases, but problem, the known cases work with homological dimension too. We do not have that hypothesis. What do we do?
The fact that E8 is its own automorphism group for this kind of problem. Explain what ways you can do it for E8, E7.
I'll get there. But yeah, the answer is tree of function. So every inner form is strong inner form. That's the secret. That's why we can do it.
I know the secret. I can.
I intend. I intend to explain actually that part. If I get. Anyway, so follow no cases of history and each time. So this, I see this is a big each time. The hypothesis on the cohomological dimension appears, which time this hypothesis is used. What do you do? Well, you replace K by extensions, finite extensions, where, and let me be vague again, where the situation, whatever that means, is trivialized, and take norms. So, okay, that's extremely vague. Let me be even worse and put this into a model. So, what do we need? We need two things. Trivialize stuff. And pile up norms. Okay. And here I'll stop being vague and try to explain what this means, but that's the model. We just need to trivialize stuff and pile up norms from these extensions that trivialize stuff. And that's the game. That's the game. We just follow the proofs that are known and start doing these kind of things. So let me try to do some sort of table here. So just put the stuff in this half. And I'm going to put trivialized by L over K if, well, so let me start with the obvious one, the one that we've been using all along. I take Z, a K variety. Well, when does it become trivial? Well, if you get points. Okay, if you get a null point, then the situation is trivialized. Actually, for torsos, it's literally that. Torsos get trivialized if you find points. What else? For instance, take homology tests. So HNKN with M a Galois module. Well, you can guess what I'm going to put here. So alpha respect to 12 is 0 in HNLN. Okay. What else? Take, since of course these guys are going to appear sooner or later, take Q a quadratic form over K. Well, how do you trivialize a quadratic form? Just say that Q over L is hyperbolic. So that's a way of trivializing. And one last example. So take V in H a Hermitian form over D as central simple algebra with involution. And here's where things start with involution, where things start to get tricky. Because this can be trivialized in lots of ways. Okay? So either, for instance, if you go to L, you can get that DL is not a central simple algebra. So you killed the algebra, you killed everything that was there. So that's a way of killing this, trivializing this situation. Or, for instance, you can stick with DL a central simple algebra, but you got something that appeared. But VLHL is hyperbolic. Sorry. Sorry, yeah. Sorry, yeah. Yeah, I should have put, yeah, I'm sorry. That's a mistake in my notes. Yeah, divisional. Yeah, of course. You're totally right. Sorry? Actually, yeah. There's 3 cases, of course. I told you there's a lot of cases. Yeah, okay. So let me just okay.
L is in DL here.
So yeah, of course. DL is not division. DL, yeah, loses the involution. Let me put it that way. Or it is a central division algebra with involution, but the Hermitian form becomes hyperbolic. So there's a lot of ways that you can kill stuff. And actually it becomes worse. I don't want to write it here, but since you're considering bound restrictions, you have to consider a K, and then you're going to consider a section L, and you're going to consider an algebra with evolution over L, so you have a quadratic extension of Ln. So what could happen? You can kill L over K, could stop being a field. Then L over N over L could stop being a field. Or then the division algebra over L could stop being a division algebra. So it's a lot of things that could go wrong and trivialize the situation. And you have to keep track of each one of these. Sounds easy, but then the second part comes, you have to pile up norms, and then it becomes complicated to actually pile them up. So yeah, there's a lot of information going on, but that's the main idea. So for instance, in the proof of the theorem, the one with the type AN, so we do follow Byron-Palimalis proof, and at some point, for instance, there's this exact sequence with bit groups, bit groups that comes up, and so you pick your emission form, you push it, you want to prove that you use it. Convolutional dimension 2 is implies that this is trivial. Okay, so for us it implies take extensions. So there is trivial. There we can come back and we take norms. And then they go back, so we find out someone that represented here that has this or that property. Because of convolutional dimension 2, okay, take more extensions of the extensions you already got, take norms, etc. So it becomes a nested argument that has like 5 or 6 levels. All right, and at some point they used, this was awful, they used the theorem of Jankowski, that again uses convolutional dimension 2, on the fact that, what was it again? If you have a reduced norm that is symmetry, invariant under the evolution, then the element actually is product of such elements, is product of symmetric elements. So we have to define, for instance, here some symmetrization. You say that to trivialize something, you just symmetrize it, or you generate it with symmetric elements, and yeah. When you try to follow the whole thing, we actually pile up like 10 towers of norms. It's just tough, but it works. Okay, so in order to give you an idea of what this piling up of norms is, I want to really explain the case of field, and that's the only thing I'm going to do, because otherwise, keeping track of the whole piling up of norms is just terrible. I hope that we will rewrite this in a better way at some point, but right now it's quite difficult to follow the whole point. So let me give. Anyway, yeah, I'm not done with this though. So this is the idea of trivializing stuff. So, what you can do after this is, so you can define. I should have written this before I started talking. Anyway, so MQZ of K, that's already defined. You know what it is. That you can start guessing what this would be, or this would be, or this thing over here, etc. So yeah, of course, you define this. It's just a subgroup of the K-theory group that is generated by norms coming from the L's that actually trivialize these different objects, and prove results as such. As here I'm going to represent a statement. So this one we can prove quite easily. So if you have convolutional dimension for it equals 2, and you get n a finite Galois module, then you get NQ of alpha over K is the whole K-theory group for every alpha in any convolutional group for n greater So the idea here, if you once again if you fix q equals 0, you're in chronological dimension 2, and you're essentially saying that here that yeah everything above 3 is trivial. It's just mainly obvious, right? But in order to get to this general statement, we have to use very powerfully the block-catch projection. But you can actually do this kind of things. Okay, so this the proof uses the block-catch projection.
Can you explain the notation on the left-hand side of the quality?
This one, right? Yeah, of course. Yeah, I would guess. Yeah, I'll write it down. Sorry. It's just that it's always the same thing and it's so long. But I'll write it down. So NQ alpha over K would be the group generated by some norms of alpha is on K, yeah. This way. For else, so I take all the norms from the extensions over K such that alpha is 2L is 0 in H and L. So that's the point. You just take norms from extensions that trivialize your object in this sense. That's it. So you have to come up with a good definition of trivialization. So that's why every time you face an object where you use the property chronological dimensions more equal than 2 to say something about this object, you have to call that situation trivial sometimes and give the corresponding definition. So we have lots of definitions that go in the same way, and then you prove theorems like this one for those objects, and then you pile up these arguments one over the other. So now I can actually try to give an example with this end. I'm not sure. No, that would be enough. That would be enough. So let me put an example of the second part, so piling up. So you can see this will be just a tower of 2 steps. Should be easy enough to follow. So let us say that we want to prove that NQ Z over K is the whole K theory group for a certain value Z. So for a G torso Z with G of type E8. Okay, and assume, because this is the difficult part, but assume the result for split G. Okay, so this is where we should follow G's proof and try to do the whole yoga that I tried to explain. If we get that, so we get the result for split G, and I'm going to show you how from this result we get this by piling up. So in the end, the whole result would be a piling up of these norms, and all the norms are going to pile up, proving the split case.
With respect to arbitrary primary extension, a very specific one. Which type of finite extension?
Any. One characteristic 0 though. So.
Sure, but less cyclic.
No, any extension. Any extension. The split case goes with single extensions. But okay. Okay, so let us prove that. So fix an element in your theory group, and you want to express it as a product of norms coming from extensions where these torsos will have rational. Okay. Okay, so first things first, G has a trivial center. That's the trick I said before. So this implies that there exists certain alpha class in H1 K G0 with G0 the split case, or with G0 split, such that G is just a twisted version of G0, twisted by the cocycle A. Okay, that's the point. We have since it has trivial center, every twisted form is just an inner, and E8 has no outer automorphism. We can actually prove that, yeah. Any non-split form is just an inner form of this type. So now you can let Y be a torsor, a G0 torsor. Representing this class alpha. Okay? Then the hypothesis, I'm assuming that the result is known for split G. So Y is a G0 torsor, G0 is split. So then I have that NQ Y, okay, is the whole K theory. Okay, so let me write down what this implies. This implies that there exists a certain bunch of finite extensions, Li over K, such that I can write X as a product I of norms from Li to K of certain Y I, and these Li's have the property that, well, there are rational points over Y in these experiments. In other words, and this is the point where it's important that we have torsors here, having points is the same thing as saying, okay, we trivialize the class. Okay? Great. So this implies that over Li, this alpha is trivial, so this cocycling gives me nothing, so this twisting process is nothing. In other words, G0 over Li is isomorphic to G over Li. And hence, Z over Li is a torsor over G0. But hey, this is split, so I can apply again. This implies that NQ Z over Li is the whole K theory group. Li. And now I can plug out norms. So let me write down the whole thing again. So this implies that for each element here, that's an element in the K theory of Li, we can write it as a product of norms. So there exists certain Mij over Li, finite extensions, such that, well, Yi, I can write it as a product over J, norms, coming from Mij to Li of certain Zij, right? And big Z has rational points over Mij. Right? Should put ZLI in principle here, but it's the same thing. So this implies immediately that X is just a product. Write the whole thing down. And Li over K of product over J of Mij over Li of Z Zij, which is in the end a product over I and J of N Mij over K of the Zij's. And so you have written X as a product of norms, and these guys live in the Mij's, and the Mij's satisfy that you have points in the torso. And so essentially you've proven that N lies in Q of Z. So yeah, that's how you pile up norms. So this is why we think we can go further than what is known from 14th Brauer. First things first, we have to follow everything that has been done. We expect to do that first, and then try to do what hasn't been done. This is the first level. We can go further in the case D8 than what is known for sex conjecture 2, and of course we would like to look at D6, D7, and D4 trilitarian, because there, for instance, it is known in the quasi-split case. So maybe you can come up with these kind of arguments to actually reduce the quasi-split case. Things are more difficult because there's a center. We don't have this treatment. But it is expected that the conjecture holds more generally and would be easier to prove an actual sex conjecture. But that's what we got for now. So let's stop here. Thank you very much.
So if I understand this correctly, your proof sort of uses the fact that sex conjectures 2 is correct or is known for a particular case, and then uses that as like a crucial tool going forward.
Yeah.
Could you for example, assume Sarah's conjecture 2 is true, and then show that all the higher ones are follow from that? Do you think that that's a strategy that would work, or do you need to use specifics about how it's true?
Yeah, I'd love to say yes, and I hope that there is a proof like that, but for the time being, no. No, we do have to follow the proof and replace cohomological dimensions more equal than 2 by some piling up norm argument.
You need particulars about the proofs of this.
Yeah, exactly. We have to follow them completely. So we have to actually read, as I told you, we have to read the whole article by Janchevsky and do the whole article again, and plug it as a tiny bit of the whole proof of Byron Parimala. So right now, just AN has like 20 pages. It's a really, really enormous argument because, yeah, you have to follow it in full detail. We do expect, I mean, I would like to have a proof that depends only on, say, cohomological arguments. That's just abstract nonsense. But that would tell you, but we're essentially doing nothing new in some sense. So if we get that, it would be a little bit disappointing, actually. But yeah, it could be true. It could be true. For the time being, we don't know how to do that anyway. So we do follow the proofs.
When we're with positive characteristics in the discussion of such conjecture 2, we just want to avoid small bad characteristics or what?
In the case of self-conjecture 1, actually,
Yes,
we managed to
that's
prove
the
stuff.
uniform case.
Yeah, we have to avoid the uniform case, that's for sure.
In the case of self-conjecture
Yeah,
2,
I would expect for it to be true, but the point, what I was going to say, in the case of self-conjecture 1, we actually proved the arbitrary characteristic case by reducing to the characteristic 0 case. So if these tools are generalizable to this case, I expect that. Then we don't even care. We prove characteristic 0, then we deal with a reduction to the characteristic 0 case. That would be intended. But maybe it's not true. Maybe we can't in this case. So I don't know. That's why we're sticking to characteristic 0 first. We want a full result there, and then we'll deal with characteristic. But yeah, I would expect that to be true. I expect us to be capable to reduce to that case somehow. No. For timing, we don't use it at all. So yeah, but then again, if the reduction argument works, we don't have to deal with the specific cases of characteristic of positive characteristic in characteristic 2 and 3. So if we can avoid that, better, right? Yeah, but that's why we reduced to characteristic 0 in the first place. The other paper went the same way. We worked out the whole characteristic 0 case first, and then we realized, hey, we can do it in arbitrary characteristics. So yeah, we reduced to that.
I have a question with regard to this finite mysterious extension K, which I guess in the end are produced by Lucchini. There exists this extension, they come from the use of norm, which uses
This is pure abstract nonsense because you assume that you have this one, which is, you use here because you assume something. But at some point when you start following the whole tower, the last one, would be blocked out. Because the last one would look like, but the theorem I wrote for cohomology classes, that one usually block out conjecture. So once you get to a cohomology class and you're killing that one, block out conjecture is here. So most of them are abstract nonsense. And at some point, when you get to the last one, you get an actual arithmetic or algebraic result, which has some juice. And in the end, it's block out conjecture for cohomology classes. Otherwise, for quadratic forms or Hermitian forms, etc., is the analog statement in higher versions.
Come from a base color restriction and such, and in the end,
in the end, it works like that. But you have to follow the things in the right order.
it can be reduced to a p-special field.
That's the kind of argument you can immediately use. In this setting, you can always just restriction argument. Then you reduce yourself to taking an L silo to an L group, and you deal with L torsion. Yeah, that's the kind of thing you can do, and you cannot do with rational points. Precisely.
There's one small filter that you have to be careful about. Since you're looking at rate restrictions, they might split into pieces, and so you need to be careful with the inductions, the way that you do it, because there are many ways to do that, and many ways that are wrong.
Yeah, exactly. each time you trivialize something, you gotta be careful which thing trivializes first. And you have to pile them up in the good order. It's a nice puzzle. It works in the end, but yeah, you have to be really, really careful because sometimes, precisely when things split, you get products. And for products, you have to prove things for every extension before you can actually plug them together. But you're in an induction process. You cannot just assume that everything has been proved for any extension. And yeah, sometimes you can actually bite your tail. It's tricky. It's tricky, but it can be done. You have to choose the right order. So yeah, well, it's a nice puzzle in general, but you have to be very, very careful about the order in which you split things. That's why I told you the last one usually is the one that actually has some mathematical deep result. Yeah. Yeah.
More questions?